Waves occur all around us. Most common, perhaps, are gravity waves in water and compressibility waves in air. Because waves in water are easy to observe, we will begin with them. Later we will see that many of the concepts we have developed with these gravity waves apply equally well to compressibility waves in gases. A surface gravity wave is a region of increased or decreased depth that moves relative to the fluid. A large amplitude wave produces a large change in depth as it goes by. When the change in depth is small compared to both mean depth and wavelength, we call it a small amplitude wave. Even when we cannot see the surface, we can detect the passage of a wave by the change in pressure at a fixed point. We can also detect it by the motion of the fluid particles. These solid particles are very nearly the same density as water and hence move like fluid particles. Note that the motion of the fluid is very limited in comparison with the motion of the wave. Here, the wavelength is comparable to the depth. In these waves, the particles move in circular paths. The diameter of the circles decreases with depth. The particles near the bottom hardly move at all. This is the pattern of fluid movement characteristic of waves on the surface of deep water. That is, where the wavelength is comparable to or less than the depth. Shallow water waves are waves with wavelength long compared to the depth. This is the characteristic pattern of particle motion for shallow water waves. Notice that the horizontal amplitude of the particle motions is nearly the same at all depths. We say that such waves are essentially one-dimensional, since the horizontal fluid motion depends only on time and horizontal distance from a reference point. Because they are simpler and yet display most of the important features of wave motion, we will use one-dimensional waves for further study. Not all waves are periodic. We can send a single step wave down the channel. And for our purposes, we may consider either a step wave that increases the depth or a step wave that decreases the depth. Note the movement of the fluid particles as a step wave passes. In the undisturbed water ahead of the wave, the fluid is at rest. After the wave has passed, the fluid is moving in the same direction as the wave at a constant speed. The passage of the wave accelerated the fluid. Watch one particle again. While the wave moves from here to here, the particle moves through a much shorter distance. These particle images were recorded at equal time intervals. So, from the spacing, it is clear that the wave is a region of acceleration. If we let the wave continue out of frame, we see that the particle is no longer accelerating, but moving at a constant speed. Fluid acceleration occurs only during the time the depth is changing. The depth in a given region can only increase if more fluid is moving into it than is moving out, a simple statement of the conservation of matter. And clearly the fluid velocity is higher here than here. Now here's a wave that decreases the depth. More fluid must be flowing out of a given length of the channel than flowing in for the depth to decrease. The particles ahead of the wave are at rest. Those behind it are moving at a constant speed. The decrease in depth is accompanied by an acceleration of the fluid. While the wave moved this far, the particle moved this distance, accelerating in the opposite direction, as our multiple exposure shows. And as the wave moves on out of the frame, we see the particle continuing to move with constant speed. What force causes the fluid to accelerate? It is a force arising from differences in pressure. Note how the pressure at the bottom of the channel increases as this wave goes by. For these shallow water waves, the vertical acceleration of the fluid is small compared to the gravitational acceleration. Thus, the vertical pressure variation is nearly hydrostatic. That is, the pressure is atmospheric at the surface and increases almost linearly with depth. The pressure difference in a horizontal direction is nearly the same at all depths, which means that the horizontal acceleration is nearly the same at all depths. As this wave passes, the pressure on a fluid particle increases. For this reason, we may call this type of wave a compression wave. Note that the fluid acceleration is in the direction of wave motion. In this wave, the fluid acceleration is in a direction opposite to the wave motion. This is so because the pressure is higher at the leading edge of the wave than at the trailing edge. As this wave passes, the pressure on a fluid particle decreases. Hence, we may call this type of wave an expansion wave, in contrast to the compression wave. In both cases, the vertical pressure gradient arises because of the gravitational force acting on the fluid. Thus, it is really gravity that causes these waves. Whenever the fluid surface is not horizontal, a horizontal pressure gradient is produced by gravity that accelerates the fluid horizontally. We have viewed the waves in a reference frame at rest with respect to the fluid ahead of the wave. Let us change our frame of reference and move with the advancing wave so that we can watch the shape of the wave. As it advances, the compression wave appears to steepen, the trailing edge overtaking the leading edge. The expansion wave, on the other hand, flattens out, the trailing edge falling behind the leading edge. Differences in local fluid velocity and depth within the wave itself alter its configuration as it advances. Where the depth is greater, that portion of the wave travels faster. We can see this variation in wave speed quite easily. Here is a depth of 1 inch, here is a depth of 4 inches, and here one of 9 inches. Small amplitude waves pass this line at the same instant. Obviously, their velocities are different, the wave in the deepest water traveling fastest. In fact, their velocities are in a ratio of 1 to 2 to 3, directly proportional to the square root of the depth. The wave speed is given by the square root of gh, where h is the depth. This fact that the wave speed relative to the fluid, the local wave speed, increases with depth is one reason why an expansion wave tends to spread out as it moves. we can describe the velocity of the leading edge of the expansion wave relative to the fluid as square root of GH1. Similarly, we can describe the velocity of the trailing edge relative to the fluid as square root of GH2. Clearly, the local wave speed at the shallower trailing edge is less than the local wave speed at the deeper leading edge. But there is another factor at work here. The local wave velocity is always stated relative to the local fluid velocity. Now, we have already seen that the fluid at the trailing edge of an expansion wave is moving away from the fluid at the leading edge. So, relative to the leading edge, the slower speed of the trailing edge is rendered even slower by virtue of a local fluid velocity there in the opposite direction. The fact that the local wave velocity increases with depth also explains why the compression wave tends to steepen. The local wave velocity is higher at the deeper trailing edge of the wave than at the shallower leading edge. Furthermore, in compression waves, the fluid at the trailing edge is moving toward the leading edge. This local fluid speed adds to the increased local wave speed at the trailing edge, causing the trailing edge to overtake the leading edge even more quickly. Watch this wave steepen in slow motion as we follow its leading edge. What happens now? Anyone who has been to the beach knows the answer. The wave topples over. Note that the toppled wave moved out of our picture, which means the leading edge of the wave is traveling faster than it was before it toppled. Let us watch the steepening again with the camera moving at the speed of the toppled wave. Note that the toppled wave continues in its turbulent condition and does not change its shape. It also travels at constant speed. The speed of the toppled wave, which is called a positive surge wave in hydraulics, depends on both the depth ahead, h1, and the depth behind the wave, h2. Here you see 3 channels with water 4 inches deep in them. We are going to send positive surge waves down these channels with depths behind the waves of 6 inches, 8 inches, and 10 inches. The larger the depth behind the wave, the faster the wave travels. In fact, it can be shown that large amplitude wave speed, that is the speed of a positive surge wave, depends upon the depths ahead and behind as follows. Square root of g times the average depth times the ratio of the depths. Small amplitude waves ahead of the surge wave move at the speed square root of GH1 relative to the fluid. If you compare these expressions, you will see that this local wave speed is always less than the speed of the surge wave. Thus, the surge wave catches up to small amplitude waves ahead of it. Small amplitude waves behind the surge move relative to the fluid at a speed square root of gh2. However, behind the surge wave, the fluid is moving. There is a drift speed of the fluid u. And the drift speed, thus, small amplitude waves behind the surge wave and moving in the same direction as the surge wave always catch up to it. In reality, these surge waves move at a fair clip. As the surge moves down the channel, there is zero velocity ahead of it and a drift velocity behind it. By moving the camera, we have superimposed on the motion a velocity equal and opposite to the speed of the surge wave. In this reference frame, the fluid ahead appears to be moving into the wave front. The wave appears stationary, and the fluid behind has a net velocity in the opposite direction to the drift speed. We say the flow is steady in this reference frame. We can produce exactly this situation in a flume. This is a stationary wave called a hydraulic jump. The structure of this turbulent wave is very complicated and difficult to analyze. However, if we consider the fluxes of mass and momentum into and out of a control surface like this, we can determine the velocity and depth behind the hydraulic jump given the velocity and depth ahead of it. The ratio of entering fluid speed to the local wave speed is called the Froude number. The Froude number ahead of the jump, F1, is always greater than unity. That is, the fluid speed ahead is greater than the local wave speed. We say the flow ahead is supercritical, or shooting. The Froude number behind the jump, F2, is always less than unity. That is, the fluid speed behind is subcritical, or tranquil. We can easily show this in the flume. A disturbance behind the jump catches up with the jump. A disturbance ahead of the jump is washed downstream into the jump. Note, this is only another way of describing the steepening effect we talked about earlier in a different reference frame. Small amplitude waves behind a positive surge wave catch up to it. Small amplitude waves ahead are overtaken. Energy is being dissipated in the turbulence and foaming in this jump. The pitot tube measures the total head, the sum of the potential and kinetic energy. Notice how the total head drops as we move through the jump. Mechanical energy is being converted into internal energy. This jump is dissipating about 1/3 of a horsepower. Below big dams, hydraulic jumps in stilling basins may dissipate thousands, even millions of horsepower. The temperature rise is hardly noticeable, however, since a total head loss of 778 feet is required to heat water 1 degree Fahrenheit. You can see hydraulic jumps all around you if you are observant. Have you ever seen this one in your kitchen sink? The water spreads out at a supercritical speed from under the tap, goes through a cylindrical hydraulic jump, moves at subcritical speed to the edge of the dish, and spills over the edge. Although gravity waves in liquids are easily seen, they're not the most common waves we encounter in fluids. Compressibility waves in gases are certainly more common, since sound waves are compressibility waves. Sound waves are small amplitude compressibility waves. A large amplitude compressibility wave is a shock wave. Compressibility waves move at very high speeds and can usually be seen only with the aid of special optical devices. On rare occasions, if the light is just right, shock waves may be seen with the unaided eye. However, we can easily detect the passage of a compressibility wave by the changes in pressure associated with it. Our ears, for instance, are very sensitive detectors of pressure changes. Indeed, we classify all small amplitude compressibility waves, whether they are audible or not, as sound waves. As a model for a gas, here you see many particles floating in the surface of water, more or less evenly spaced. The number of particles per unit of surface area represents the density. As a compression wave comes along, you can see the particles accelerate in the direction of the wave motion, and you see the density increasing, that is, the particles moving closer together. Much of what we have shown you concerning one-dimensional gravity waves applies equally well to compressibility waves if we simply replace the depth of the fluid h by the density of the fluid rho. In fact, a compressibility wave may be described as a region of increased or decreased density that moves relative to the fluid. Just as depth is proportional to the amount of fluid per unit length in an open channel, so density is proportional to the amount of fluid per unit length in a closed channel. The fluid flowing into this length of open channel increases the depth. The fluid flowing into a length of closed channel increases the density. In a compressibility wave, the pressure depends on the density. Just as in a gravity wave, it depends on the depth. Although surface gravity waves and compressibility waves behave quite similarly, they are propagated by entirely different physical mechanisms. The fluid acceleration in gas waves is due to elastic forces associated with the compressibility of the fluid rather than gravitational forces. The speed of a small amplitude isentropic compressibility wave increases with density, just as the local wave speed of a surface gravity wave increases with depth. This increase of sound speed causes compression waves to steepen. Gradients increase in the wave. What happens when these gradients become very high? That is, when the wave becomes very thin. The compressibility wave cannot topple over like the surface gravity wave. Instead, the density and velocity gradients reach limiting high values in a thin region and remain constant. By looking from above at only the inflow and outflow of an hydraulic jump, we can gain an impression of the steep velocity gradient. In compressibility waves, these limiting high gradients are determined by the effects of viscosity and heat conduction, which up to this point we have been able to ignore. The reason that viscous forces become significant here is that fluid particles going through a steep wave experience high rates of deformation. Viscous forces are proportional to the rate of strain. Hence, viscous forces become significant in a steep compression wave. The steepening tendency is opposed by the action of viscosity and heat conduction, and a limiting steep wave results, called a shock wave. Stationary shock waves can be produced in a supersonic wind tunnel. Here the gas is moving at supersonic speed ahead of the shock, Mach number greater than 1, and at subsonic speed behind the shock, Mach number less than 1. This is analogous to the stationary hydraulic jump we saw in the flume, with fluid moving at supercritical speed ahead of the jump and subcritical speed behind it. Recall that the total pressure, total head, dropped in going through a hydraulic jump. In the same way, total pressure drops in going through a shock wave, because some of the mechanical energy is changed into internal energy by the dissipative action of viscosity and heat conduction. Unlike the hydraulic jump, a shock wave is extremely thin, on the order of a few mean-free paths thick, about 1/1,000,000th of an inch at room temperature and pressure. A moving shock wave is what you hear when there is an explosion. It is the thunder that accompanies lightning. It is the sonic boom you hear from a supersonic airplane. We can produce moving shock waves in the laboratory in a shock tube like this one. We put high pressure gas on one side of a frangible diaphragm and low pressure gas on the other side. The diaphragm is made of celluloid sheet. We break it with a knife like this. So with high pressure gas on this side and low pressure gas on this side, when we break the diaphragm, we create a shock wave which moves at supersonic speed down the tube. By pulling a gate in the wave channel, we can produce a positive surge wave. This is analogous to the shock wave in this tube. This end is open, and we have placed streamers here to make the motion of the air visible. Now I will break the diaphragm. You noticed the wind behind the shock wave, just like the drift speed behind a positive surge wave. An atomic blast sends out a spherical shock wave, followed by a strong wind, which is the air moving at the drift speed. We can produce very strong shock waves in this shock tube. The high pressure section is here. The low pressure section is this Pyrex tube. The temperature behind a very strong shock wave can become so high that the gas molecules are torn apart, dissociation, and even electrons stripped off the atoms, ionization. Ionized gases emit light, and hence this phenomenon is easily seen. The diaphragm is located here. This is what a diaphragm looks like before it is broken, and this is what it looks like after it is broken. You can see that we're dealing with very strong pressure forces. We have argon in the low pressure section of the tube. You will see the shock as the argon ionizes. I'm going to turn down the lights. You watch the tube. Now I will break the diaphragm. So far we have concentrated on one-dimensional waves. Two- and three-dimensional waves involve the same basic concepts, but can become very much more complicated. These remarkable pictures were taken at nearly 400,000 frames per second. This sequence shows a normal shock wave passing over a wedge. Here, a shock wave passes over the sharp edge of a flat plate. Notice the vortices produced at the sharp edges and the great number and variety of shock reflections and interactions. We have shown you some wave phenomena in fluids, chosen to emphasize the basic concepts of wave propagation. First, the local accumulation of mass, which is due to depth changes in the gravity wave and due to density changes in the compressibility wave. And finally, restoring forces, pressure forces, which are due to depth gradient in the gravity wave and to density gradient in the compressibility wave.